In today's session, we will be discussing about some examples, numerical examples on stresses in bars of varying cross sections. Bars of varying cross sections. So the computation of stresses and the loads that are shared by different portions of the composite bar, that we will be discussing in today's session. As first example, let us take one problem. Determine the stress in each section of the bar shown in figure when subjected to an axial tensile load of 20 kilonewtons. The central section is 30 mm square. The other portions are of circular sections, their diameters being indicated in the figure. What will be the total extension of the bar? And the material of the bar has Young's modulus of 210 giganewton per meter square. So the given bar consists of three portions, the end portions being circular in cross section and of diameters 20 mm and 15 mm, and the central portion is of square cross section of size 30 mm sides. So the lengths are given as 250 millimeters for part 1, 100 mm for part 2, and 400 mm for part 3. So this composite bar consisting of different portions with different cross sections is subjected to a tensile load of 20 kilonewtons applied at the ends of the bar. So let us name this as A, B, C, D, say. Portion AB, portion BC and portion CD. Here AB and CD are circular and BC is square cross sections. So the total entire bar is subjected to tension. Okay. So if you consider the free body diagrams of each of this part 1, part 2 and part 3, each of them will be subjected to the same tension 20 kilonewtons. Okay. So if you consider the free body diagrams of this part 1, which is subjected to a tensile force of 20, part 2 also is subjected to the same tensile stress, tensile force 20 kilonewtons, and part 3 also subjected to a force of 20 kilonewtons, tensile force. Understand? So here, the stresses in each bar we calculate. The stress in bar 1 is given as load by area of cross section of portion 1. Similarly, stress in bar 2 is load, again 20 kilonewtons, by area of cross section. Here the area of cross section is square, so 30 into 30. Here circular, pi by 4 into square of diameter. Similarly, here the cross sectional area is pi by 4 into d square. Okay. So the stresses are different. The tensile force is same, but the stresses are different in each section. Okay. So if the stress in bar 1 is represented as say P1, and stress in portion 2 is P2 and stress in portion 3 is P3. Then P1 is given by P by A1. A1 is cross-sectional area of portion 1. Similarly, P2 is P. P is the tensile force. It is same 20 kilonewtons for all the three portions by area of cross-section of this portion, which is a square of 30 mm sides. And here the cross-section is a circle of 20 mm dia. And here the cross-section is a circle of 15 mm dia. Okay. And what is P3? The stress in portion 3, load, tensile load by area 3, pi by 4 into 15 square. Okay. Now the calculations are shown here. So stress in section 1, that is P1, is load 20 kilonewton by area, pi by 4 into d square. Okay. So the units are taken care. So we are converting the units to meganewton per meter square. Finally, meganewton per meter square means Newton per mm square. This is also same as Newton per mm square. Okay. Megapascals. It is also written as megapascal. 1 pascal is 1 Newton per meter square. Isn't it? So, the stress in portion 1 is 63.66 megapascals and in portion 2 it is 22.2 megapascals and in portion 3 it is 113.2 megapascals. Okay. So knowing the stresses in various sections, we can find now the elongations of these portions. Elongations of these portions. Okay. Total extension of the bar is elongation of bar 1, elongation of bar 1, say delta 1, and elongation of bar 2, say delta 2, and elongation of bar 3, delta 3. Okay? Because all are subjected to tensile force, all the portions will be extended. Elongation takes place in each of the portions 1, 2 and 3 being subjected to tensile force. Okay? So, delta 1, how will you get the elongation delta 1? Delta 1 is PL by AE, PL1 by A1E. L1 is the length of portion 1, that is 250 mm, and A1 is area of portion 1. Okay? Similarly, delta 2 is PL2 by A2E. Here P is same. If P is different, then we will take P1, P2, etc. General equation, we can take P1 L1 by A1 E. E is same because the material is same for all the three portions. If material is also different, then we can take E1, E2 and so on. Most general expression. Okay. So this is P3 L3 by A3 E3. The E is material property. So material being same, E will be same for all the three portions. If different materials are connected, then you may need to take the corresponding Young's modulus values. Here Material is same, so E is same for all the three portions. And load is also same. Load is also same. So P1, P2, P3 all are equal. Okay. So by this equation, you will get delta 1. You know the load, you know the length, you know the area and Young's modulus. So you can find delta L. Total extension of the bar is sum of these three elongations. Okay. So like that, we can find the stresses in bars of varying cross section. In bars of varying cross sections. Okay. Now we'll take one more example. We'll take second example. Okay. So here the second example, it is something like this. Having three different portions here also being rigidly connected between the two supports. Okay. A circular steel bar ABCD rigidly fixed between A and B is subjected to axial loads of 50 kilonewtons applied at B as shown and 100 kilonewtons applied at C as shown in the figure. Okay. Now the Young's modulus is same for all the three, which is 207 kilonewton per mm square. 207 kilonewton per mm square. And the lengths and diameters are given 300 and 380 over 60. And diameters D1 25 millimeters. We call it L1, L2, L3, and D2 is 50 mm and D3 is 75. D3 is 75 millimeters. Okay. So this is what is given. The ends A and D are rigidly fixed between the supports. So here the total elongation of the bar is 0. The total elongation of the bar is 0 because the ends are rigidly fixed. There will be no change in length. Okay. But individual portions A, B, B, C, C, D, they may get elongated or contracted. Okay. And one portion may get elongated, the other one may be get decreased, contracted. Okay. Depending on the stress to which it is subjected, whether it is tensile or compressive. Okay. Whether it is tensile stress or compressive stress. This clear. So the how to proceed is, we consider now the free body diagrams again of portions A, B, B, C and C, D. Okay. So the 50 kilonewtons which is applied at B is shared between the portions BA and BC. This 50 kilonewtons is shared among the members BA and BC. Similarly, the 100 kilonewtons load which is applied at C is shared among the members CB and CD. Okay. So let P1, P2 and P3 be the forces in portions A, B, B, C and C, D. Okay. So we can calculate the areas. Being circular, area is given as pi by 4 d1 square, which comes out to be pi by 4 into 25 square, that is 491 mm square. Okay. And A2 is pi by 4 into d2 square, that is 50 square, and its value is 1963.5 mm square. A3 is pi by 4 into 175, sorry, diameter of portion 3, that is 75 square. So this comes out to be 4417.9 mm square. Okay, 4417.9 mm square. So now, as we have seen, P1 is the load shared by portion AB, and let P1 be the stress in portion AB, which is given as P1 by A1, and delta 1 be the change in length, maybe elongation or contraction. That's why we take change in length. It may be decrease or increase. Change in length of portion AB. Similarly, let P2, capital P2, small p2 and delta 2 are the corresponding values in portion BC, and P3, small p3 and delta 3 are the corresponding values in portion CD. Okay. Now, considering the free body diagrams, if you consider the first portion AB, which is of diameter D1, let this be subjected to a tensile force of P1, and actually we have a load of 50 applied at B. We have a load 50 kilonewtons applied at B. Okay. Now, here we have a load applied at C, 100 kilonewtons load applied at C. Now, P2 be the force in member 2, that is BC. Now consider member 3, CD, which is subjected to a compressive force of P3. Okay. Now, this 50 kilonewtons is actually shared between the members BA and BC. So here P1 is the load shared by BA and P2 is the load shared by BC. So if you observe this, P1 plus P2 is equal to 50. This one relation we have P1 plus P2 equal to 50. Okay. Similarly, coming to this, P3 minus P2 is equal to 100. This is another relation we have. Okay. Or P3 equal to 100 plus P2. P3 equal to 100 plus P2. P1 is equal to 50 minus P2. P3 is equal to 100 plus P2. Okay. So these are the two relations we have between the forces P1, P2 and P3. So now we have one more relation. If you observe this, member AB is subjected to tension. That means it gets elongated. Let delta L1 be the elongation of portion AB. And coming to BC, it is subjected to compressive force of P2. So it gets contracted by delta 2. That means decrease in length takes place for member BC. Decrease in length of BC. And similarly, delta L3 is decrease in length of CD. Decrease in length of CD. So here there is net deformation of the member is 0 because the ends A and D are fixed rigidly. There will be no change in length of the member as a whole. So the elongation of the bar AB must be equal to the sum of the decreases in length of members BC and CD. So this is another relation we have. Delta L1 equal to delta L2 plus delta L3. Increase in length of member AB equal to sum of the decrease in length of BC and decrease in length of CD. Okay. So this is another relation we have. So now what is delta L1? We can find now delta L1 in terms of P1. Delta L1, which is the elongation of member AB. What is the elongation of member? P1 L1 by A1E. Isn't it? P1 L1 by A1E. So what is the length? P1 is 50. P1 is 50. L1 is 300 mm. Let it be in millimeters only. 300 by A1. 491 millimeter square into E. So E should be in kilonewton millimeter units. 50 kilonewtons, we are taking load in kilonewtons. So E value we can take as 207 only kilonewton per mm square. 207 kilonewton per mm square. Here load P1 is unknown actually. It is not 50. So P1 is unknown. P1 into 300 by 491 into 207. Okay. And delta L2 is P2 L2 by A to E. This is decrease in length. So P2 into L2 is 380. The length of member BC is 380. So P2 L2 by A2. The area of member BC is how much? The area is 1963.5 into 207, and delta L3 is P3 L3 by A3E. So P3 into L3 is 460 by A3 is 4417.9 into 207. Now substituting these values, delta L1 equal to delta L2 plus delta L3, that is P1 into 300 by 491 into 207 is equal to P2 into 380 by 1963.5 into 207 plus P3 into 460 by 4417.9 into 207. So this is third equation in P1, P2 and P3. Okay. So we substitute the values of P1 and P3 in terms of P2. Replace P1 by 50 plus P2. Okay. And replace P3 by 100 plus P2 in this equation 3. So replacing P1 by 50 minus P2 and P3 by 100 plus P2 and solving this for P2, we will get the value of P2 as 22.16 kilonewtons. Okay. That means we replace P1 by P2 minus 50. 50 minus P2. Okay. 50 minus P2 and P3 by 100 plus P2. By substituting these values, you will get P2 equal to 22.16 kilonewtons. Okay. And now from this relation, you will get P1 and P3 also. So what is P1? 27.84. Okay. 27.84. And P3 is 122.16 kilonewtons. Okay. So knowing this, these are the loads shared. So the 50 kilonewtons applied at B is shared as 27.84 for portion AB and 22.16 for portion BC. Similarly, the 100 kilonewtons applied at C is added by this 22.16 because both are in the same direction. So 122.16 is the load taken by CD, portion CD. Okay. So knowing these values P1, P2, P3, we can find delta 1, delta 2 and delta 3. the changes in length of portions AB, BC and CD. So which gives delta 1 as 0.08 millimeters, delta L2 is 0.02 and 0.06 millimeters. Okay, so that's how we solve the problems of bars of varying cross sections. Okay, this is the end of session. We discuss some more examples in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.